Alright, hello class. This is the first video in a series of math skill videos, starting with how you determine the number of significant figures in a measurement. This is from your math practice packet. We're going to go over a few examples from number 1, but before we do that, let's review our rules for significant figures. There are a few. Hopefully it'll be more clear as we go through the questions, and I'll refer to these rules. So the first rule and the easiest rule is that all non-zero digits are significant. So if you have a number like this, 721 millimeters, since none of these are zeros, all three of those digits are significant. Same thing with this number, 2,398, all four digits are significant. And then the last one is kind of a tricky one because it's a number written in scientific notation. But when you have a number in scientific notation or a measurement in scientific notation, you only look at the numbers before the factor of 10. So you would just look at this number, and it's 3.4. Since neither of those are zeros, they're both considered significant figures. Okay, so that's probably the easiest rule. The next rule talks about zeros that are between non-zero digits, and I refer to this as the sandwich rule. And it's a pretty easy rule because if you think about the idea that digits that are significant can't be significant and then non-significant and then significant again, they're all going to be clumped together. So if some zeros occur in between some non-zero digits, they must be significant. So a number like this, that zero is sandwiched between non-zero digits, so it makes it significant. And you could put a bunch of zeros in there, like this number 2001. Those two zeros in the middle are being sandwiched by the 2 and the 1 on either end, and so it makes the zeros significant. So you'll see in the next couple of rules that zeros are where things get tricky, but zeros that are sandwiched should be pretty clear that they are significant. Next rule is when you have zeros alone on the left. So since we talked about the sandwich rule, zeros that are in the middle of non-zero digits will be significant. It's when you have zeros on either end, the left or right of a number, that can get tricky. So the first rule is about zeros that are alone on the left. So for example, these zeros here, or these zeros here, notice that they're just hanging out on the left side of the number with no other non-zero digits. When you have zeros like that, they're just placeholders. All they're doing is shifting the meaning of the number left or right along the decimal place values. So they're making the number bigger or smaller by factors of 10. So because of that, only in this number, only the 5 and 3 are significant, and in the bottom number, only the 2 is significant. So when you have zeros alone on the left, they are never significant. Doesn't matter about these decimal points. If they're hanging out alone on the left with no other non-zero digits, they're not significant. If you have zeros alone on the right, it's a little bit trickier. You have to look for a decimal point. So if you have zeros hanging out on the right side of a number by themselves, you have to look for a decimal point somewhere, anywhere in the number. If there is a decimal point in the number, then it makes the zeros on the right significant. So in the first example, we have a 0 hanging out by itself over here with no non-zero digit on the other side. Because there's no decimal point here, that 0 is just a placeholder like the ones that we saw up here. All it's doing is making this number bigger by a factor of 10. It's just shifting the 1, 2, 1 over on the decimal place values. So only the 1, the 2, and the 1 here are significant. So in other words, that 1 here was the last estimated digit in this measurement. The 0 is just changing the size by a factor of 10. So in this example, the 0 is just a placeholder because there's no decimal point in the number, so only 3 sig figs. In the next example, there are zeros hanging out on the right here, but notice that there is a decimal point in the number, and so the rule says if there's a decimal point, it makes those zeros alone on the right significant. So in this one, all three of these digits are significant, and the reason, why else would that decimal point be there other than to show that there is accuracy in this measurement? So these zeros are significant, and whoever made this measurement is telling you that these zeros are showing you accuracy by adding that decimal point there. Same thing with this number. Because the decimal point is there, these 3 zeros hanging out on the right side by themselves are all significant, so you have 4 sig figs here. The last rule is just kind of an extra rule to not forget about. It will show up every once in a while. If you have counting numbers, these aren't measurements. These are exact counts. And so they will have an infinite number of significant figures, so 10 pairs, 76 dogs, or in the future when we start using conversion factors, those will also be considered as exact and will have an infinite number of significant figures. So this will pop up every once in a while, and we'll do an example on your packet. So let's do a few questions from your packet. I'm going to kind of jump around a little bit here and refer to some of the rules. So the first one, let's do 1C, this number here. Remember, the zeros are where things get tricky, so your eyes should always kind of go to the zeros. But these zeros here are being sandwiched. So this goes back to this rule, the sandwich rule. If the zeros are sandwiched, they're significant. So in this one, all 4 of these digits would be significant because of the sandwich rule. In the next one, 1D, 270 pairs, be very careful and read your units. This is one of those tricky ones where pairs is a counting number. It's not a measurement. So even though we could look at the 270 and try to look at the Sig Figs, it's not a measurement, it's a count, it's an exact number, and so the number of significant figures is infinite, or you can write infinite. Okay, so that one's a little bit tricky. 1F, 105,000 seconds. So this first 0 here is being sandwiched. So because of the sandwich rule, it makes that 0 significant. The other zeros here are alone on the right. So if we look back to our rule about zeros that are alone on the right, it says that there needs to be a decimal point somewhere in the number to make them significant. So if we look for a decimal point in that number, it is not there, which means that these zeros alone on the right are just placeholders. So the only digits that are significant are the 1, the first 0, and the 5. So there are only 3 Sig Figs in that number. These zeros are just placeholders. And this will make more sense when we learn scientific notation. We can write this number without those zeros, and it would be the same number. So let's jump over here to one that is in scientific notation. 1H, 2.00 times 10 to the negative third milliliters. And remember, when we have a number in scientific notation, we just want to look at this part of the number, not the factor of 10. And this number, 2.00, also has zeros alone on the right. So if we look back at that rule, if there's a decimal point, the zeros are significant. So since there is a decimal point in this number, it makes those zeros significant because they're showing accuracy. So here, all 3 of those digits are significant because of the decimal point. And the last one we'll do, number 1K, we have a bunch of zeros here alone on the left. So if we look back at our rule, zeros alone on the left are never significant, no matter how many zeros there are, no matter if there's a decimal point. If they're hanging out by themselves, these zeros are not significant. The only digits that are significant here are the 7 and the 8. So there are only 2 Sig Figs here. All right, hopefully that helps you starting out counting significant figures.